Now that we found how to find the nth term of any series, let's derive the formula for finding the sum of these series. First, we will derive sum of the arithmetic progression series. A generalized arithmetic progression would look like this: A plus D, A plus 2D, A plus 3D, where A is the first term, D is the common denominator. So, sum of this series is Sn, which is the sum of the series. A plus D plus A plus 2D plus A plus 3D. If you remember, nth term is A plus n minus 1 into D. Let me reverse this series. We get first term as A plus n minus 1 into D. Second term A plus n minus 2 into D. Third term A plus n minus 3 into D. Last term would be A. After reversing the series, the first term will have n minus 1. Subsequent term should have 1 less than n minus 1. Hence it is n minus 2. And next term will have n minus 3. And the last term is A. Add both of these series. Sn plus Sn is 2Sn. Addition of first term of both the series is A plus n minus 1 into D, which is 2A plus n minus 1 into D. The addition of second terms in both the series also give 2A plus n minus 1 into D. This is the case with each term. We get 2Sn equal to 2A plus n minus 1 into D plus 2A plus n minus 1 into D plus 2A plus n minus 1 into D, and last term is also 2A plus n minus 1 into D. 2A plus n minus 1 into D is added n times in this series. Hence it is n into 2A plus n minus 1 into D. 2Sn is equal to n into 2A plus n minus 1 into D. Hence Sn is equal to n in the bracket 2A plus n minus 1 into D divided by 2. So, given number of elements in the series and first number and denominator, we can find the sum of all the numbers in the series. Note, we don't have any formula for finding the sum of the elements in harmonic series of numbers. Let's find the sum of a geometric series. Geometric progression in generalized term is AR square, AR cube. If you remember, nth term of geometric progression is A into R to the power n minus 1. Hence, sum Sn is A plus AR square plus AR cube plus so on, and the last term is A into R to the power n minus 1. Multiplying this series by R, we get R into Sn equal to AR plus AR square plus AR cube, so on, A into R to the power n minus 1, and the last term would be plus AR to the power n. Subtract first series from second series. It is Sn minus R into Sn. If you notice, except first term in first series and last term in second series, all other terms cancel each other. So, end result is Sn minus R into Sn equal to A minus A into R to the power n. Take Sn as a common factor. It is Sn in the bracket 1 minus R. In RHS, take A as a common factor. It is A in the bracket 1 minus R to the power n. Hence, Sn is equal to A into 1 minus R to the power n divided by 1 minus R. This formula takes different form based on the value of R. When R is smaller than 1, then the denominator is greater than 0. So, this formula remains same. When R is greater than 1, then the denominator becomes smaller than 0. This doesn't make sense. So, in such a case, multiply and divide both numerator and denominator by minus 1. Sn is a into 1 minus r to the power n divided by 1 minus r. Let's multiply both numerator and denominator by minus 1. We get a into r to the power n minus 1 divided by r minus 1. When r is greater than 1, we should use this generic form. Consider another case when r is equal to 1. Sn is equal to a plus ar square plus ar cube plus so on, and the last term is plus a into r to the power n minus 1. Replace r with 1. We get Sn equal to a plus a plus a plus a, and the last term is also a. Basically, we are adding the a n times. Hence, it is n into a. So, when r is equal to 1, Sn is equal to n into a. Let's consider last scenario when n is infinity. That is basically when series is infinite series and r is smaller than 1. In all the previous cases, n was finite, that is, number of elements in the series were limited. Let's see what will be the sum if the number of elements are infinite. Let's take an example. N equal to infinity and r is equal to 1 by 4, which is smaller than 1. The generic formula of sum of the series is Sn equal to a into 1 minus r to the power n divided by 1 minus r. Replace r and n with respective values. It is a into 1 minus 1 by 4 to the power infinity divided by 1 minus 1 by 4, which is 3 by 4. 1 by 4 to the power infinity is such a small number that it can be neglected and considered as 0. So, the generic equation of finding sum of the series become Sn equal to a divided by 1 minus r. We have derived the formula for calculating the sum of geometric series in all possible conditions.